All right, everyone. Excuse me. This is our AP Physics 1, Unit 1, One-Dimensional Motion, Part 1, required video lesson that I want you to listen to. You will hear bells and things. We will go over some of the vocabulary that you should know as you walk in for class tomorrow, and we will go over parts of the notes right now, but most of the workout examples we'll go ahead and do in class. So you won't see this in this recorded video. So just kind of skip through as you see different parts and fill it in as needed, and we'll go from there. So, first thing that I want to talk about is the difference between distance and displacement, which are two vocabulary words. And in order for anything to actually, for us to know it's moving, we have to compare it to a frame of reference. For example, when you see a car go by, the reason you know it's moving is because there's like trees and buildings and things in the background that aren't supposed to move, that are changing in reference to it. So that's what frame of reference is that it's a comparison point to an object so that you can tell it's in motion. All right? Now, distance and displacement, I'm going to use my little ladybug here to kind of do a visual of the difference between distance and displacement. And you'll notice that the distance is in blue and the displacement is in red. Now the blue is tracking every single step the ladybug takes, but the red is only going from the very beginning to where the ladybug is at that position. So it's just making a straight line shot from A to B, okay, by the time we're done. So distance is really just how far something travels, every step it takes, and it's just a value, okay? Whereas displacement is how far something travels in a given direction. So that means just from the beginning to the end, how much did it move? If we retraced those steps or stepped back over them, changing directions, then they get canceled out, because that's when we start talking about positive and negative motion. And when you add positives and negatives together, they start to cancel each other out. If we pulled this blue line and made it completely straight, the distance would be a lot further than the displacement, okay? But displacement has directional information, distance does not. That leads us into scalar versus vector quantities. And you could have put that distance and displacement information in your scalar versus vector section on your notes. Scalar values have magnitude only, and magnitude really is just numbers, all right? So, for example, if I say 10 miles, 20 kilometers, 100 meters, any of those things are just magnitudes. So, and they're scalar values. They're magnitudes and just scalar. So that would mean distance is a scalar value. Whereas vector values are described more with both magnitude, so it's a number, and a direction, like 10 miles north, or 20 steps to the right, or 5 steps northwest. We'll talk about angular motion too, so that'll become a part of our direction. But that also means that displacement is a vector value, because it's going to have a number and a direction as well. So I have my little jogger girl here, and she goes from point A to point B and then point C. And at first, I just want to know how much distance she traveled. And so if I want to just know how much distance she traveled, I'm going to take every segment into consideration. So she's going to go from A to B, she'll go 300, and then from from B to C, she'll go another 100. So 300 plus another 100 would be 400 meters overall. But her displacement is just from where she began to where she ends. So that's just from A to C. Well, that movement is only 200 meters, but it's 200 meters to the right. It has to include both the magnitude, which is the 200 meters, and the direction, which is the right. Now the skier is going to travel from A to B, and then B to C, and then C to D. If that's the case, I want to know how much distance they've traveled. So that means I have to take the whole 180 that they travel from A to B, plus the 140 that they travel from B to C, plus the 100 from C to D, in order to come up with 420 meters. It's just value, it's scalar, it's distance. Now, if I want to know what their displacement is, then I just want to go from A to where they finished. So that's to A to D. So that's just 40 and 100. So that's 140 to the right from where they started. So again, that's magnitude and direction because it's displacement. So those are our differences between our scalar and our vector and distance and displacement. All right, so this first example we have, we're going to consider a body that accelerates from 4 meters per second to a negative 4 meters per second in 10 seconds. And I really just kind of want you to plot that body's velocity versus time graph, which you guys should be able to do since that was just the test that we finished. So take a moment, pause me right here, and then do that on your paper, okay? Hopefully you went ahead and did that, and it should look a little bit like this. So now that we're back, that's what it should have looked like. And how far did the body move during that interval? Well, we are supposed to find the area under the line to figure that out. So we'd have to find these two triangles and each one of them. Now, when we do the 1/2 base times height, we're doing 1/2 velocity times time. And so the very first one, they moved a positive 10 meters. Okay, so 4 meters per second. And then the second one, they moved a negative 10 meters. So they actually had a displacement of 0 meters. But they actually traveled 20 meters overall. So it depends on whether we're looking at the displacement or the distance that they traveled. So describing it qualitatively, how did they move? Well, they moved in a negative direction. They were moving the positive direction to a stop, and then they moved in a negative direction. So they switched directions and moved the other way and sped up. So they slowed down and then they sped up is really what happened. All right? That's qualitatively what happened. So problem-solving guidelines, and I really just listed these as well, so I'm going to go over them really quick. But this is how I give you partial credit. So every time you're doing your homework problems, I give you all the answers, so I'm expecting to see the process. That process is going to be that you make a list of variables. What do you know? What are your known information? Make sure that you list that. Tell me what variable it stands for and what information that is. Then convert units. Everything should be in meters and seconds and kilograms for what we're going to be doing this year. Then make a sketch if you really need to. Sometimes you will and sometimes you won't. It'll depend on the problem that we're doing. Identify what you need to figure out. So what are you trying to solve for? This is really important, these first 4 steps, because they're really how you start to figure out which equation from the formula chart you need to be able to use. Then you're going to solve the equation for the unknown. So I want you to actually pull the formula from the formula chart and rearrange it before you plug in numbers. Okay? Be consistent with your units. Make sure that all the units are the same so that they'll be able to cancel out. Check to make sure your answer is reasonable. Does it make sense? Okay? Did you get a negative time? Can you get negative time? No, that's not reasonable. So check for little things like that when you get done. Physics problems take practice. The more you do, the easier you'll be. I will always give you harder problems in your homework than you're really going to see on your test, because you can come in and ask me questions about the homework. So that's always important to make sure you do your homework, because then you're more prepared for the test. So acceleration, the definition of acceleration, and this is kind of skipping a lot of your examples and going more into your equations portion. Acceleration is the rate of change of velocity, and it really has the change in velocity is the final velocity minus the initial velocity. Initial velocity, I say, is VO. And one way to write the formula is like this. If you look on your formula chart under mechanics, you'll see that the very first formula is this one, but it's written a little differently. It's manipulated to say Vx equals Vx naught, plus a t. That's really, the x's are just saying that this is all in the same plane with each other. So if this would be talking about the x-axis, we could change that to the y-axis as well. But they both the velocities have to be in the same plane, and that's going to be important as we go along. But these are really the same information, This could also be written as VF equals VO plus AT. So I want you to be able to see all of them and the different manipulations, but this is the one that's on the formula chart. So that's what you need to know. This one's beneficial if we want to really just solve for acceleration. You already have it manipulated, but you have to realize that this is what you're going to be given on the AP test. All right? Now, our units for velocity and speed are really the same sort of thing, except speed's just a magnitude value and velocity is a vector value. So they will always be, our velocities will always be in meters per second, and our time will always be in seconds. So your units on your acceleration will always be meters per second squared, because your velocity is in meters per second, over seconds. And really meters per second is a meter per second squared. So that's one of the equations that you can write down. Now, do you remember in your notes, we already answered the following in your notes. So you just might want to find somewhere to put this in your notes. You have that very back page that you could actually write this down on. It's blank. You walk exactly 250 steps north. Turn around and walk 400 steps south. How far are you from your starting point? Well, think about it. We start here, and we go 250 steps this way. That would be a way of thinking about it. We're then going to turn around and walk 400 steps this way. So, how far are we from our starting spot? Well, we just want to go from here to here, roughly. So, that would end up being 150. Because when I take 400 and I minus 250, okay, I'm going to end up with 150 steps. So, is this, and I'm actually south of where I started. Is this a distance or a displacement? Well, if I just say 150 steps, then that is actually a distance, if I'm just asking for my starting spot. But if I say 150 steps south, that's really a displacement. If I really wanted to know the distance that I traveled, I would have said that that was 650 steps. All right? A small car is rolling along a horizontal surface that's 2.25 meters in a time of 1.35 seconds. What's the average speed of the car? I want you to go ahead and take a little bit of time to do that. That one's not actually one of the examples here, but go ahead and take some time to do that one. Go ahead and just pause me right here, do that one, and make sure you include all your steps. All right? So now that you've done that, you need to check for some things. Did you make a list of variables that had something like d equals 3.25 meters and t equals 1.35 seconds? And then you're looking for speed, so you might want to write f equals question mark. How do you find speed? Well, we've talked about that. Speed's really just a velocity. So it's a change in distance divided by a change in time. Okay? So you would then write that formula, S equals d over t. That needs to be written on your paper. You then need to plug in the information. 3.25 meters divided by 1.35 seconds. That work, even though it's going to be done in your calculator, must be on your paper, okay? And the units must be included. Then you're going to do that calculation in your calculator. So your 3.25 divided by 1.35, and you should have come up with an answer that would have been 2.41 when it was rounded properly, and that would have been meters per second. So you would have needed to have your answer rounded correctly, and then have your units of meters per second with it as well. Those are the 5 things that I'll always look for. A list of variables, a formula, your actual work that you're going to plug into your calculator, your answer rounded correctly, and then the units. Okay? So make sure you just box that answer, and we can go from there. Okay? Now, some other equations that you just might want to make sure that you're aware of. If we're dealing with constant speed, like I said, that's d equals v times t. This is the one formula that's not on the formula chart that you're just kind of expected to know. Speed also is just a distance divided by time. So you're just kind of expected to know that. It's not in your formula chart anymore. Then, constant acceleration, the formula that we have at the very first one. So that means that the acceleration is never going to change. When it's the same, you'll have this formula, which is on the formula chart. We also have this formula, which is also on the formula chart. The only difference with this on the formula chart is that we have a D here instead of an X. So this is actually the second formula. And again, we can talk a little bit about that and how they're different as we continue to go along in class. And then our last one is this one. And again, it's the third one on your formula chart, but I've just kind of taken out the X's because everything is in the same plane. So I have my final velocity squared equals my initial velocity squared plus 2 times my acceleration times my displacement, which they show in your formula chart as x minus x naught. So all of this could have been put in your notes so that we'll be ready to go with examples tomorrow, and I'll be excited to see you in class. Bye!